Welcome to all. Welcome to all. Today we will look into shafting or design of shaft. When the shaft subjected to bending moment only. This is the condition. We will discuss the design of shafts subjected to bending moment only. When the shaft is subjected to bending moment only, then the maximum stress tensile or compressive is given by M by I. M by I is equal to sigma B by Y. M by I is equal to sigma B by Y, where M is equal to M is equal to M is equal to bending moment and I is equal to moment of inertia of cross-sectional area of the shaft about the axis of rotation. Here we can use this equation. M by I is equal to sigma B by Y, where M is equal to bending moment, I is equal to moment of inertia, sigma B is the bending stress, maximum stress tensile or compressive, then Y is equal to that distance from the neutral axis to the outermost fiber. Y is equal to distance from the neutral axis to the outermost fiber. Sigma B is the bending stress. Okay, then I is equal to, for a round solid shaft, moment of inertia for I is equal to moment of inertia, that's equal to pi d raised to 4 by 64. We have already discussed this term in strength of materials in the previous semesters. The moment of inertia of the solid shaft, I is equal to pi d raised to 4 by 64, and Y is equal to d by 2, where d is the diameter of the shaft. Then substituting these two values in the equation, M by I is equal to sigma B by Y, where M is equal to pi by 32 sigma B into d cube, or pi d cube by 32 into sigma B. Pi d cube by 32 into sigma B is equal to bending moment. Then from this equation, diameter of the solid shaft D can be calculated. Okay, then when the shaft is a hollow shaft, then moment of inertia is equal to this one. Instead of D, we can use dO and di, d outer and d inner. dO means outer diameter of the hollow shaft, di means inner diameter of the hollow shaft. Then I is equal to this one. Then we can use another term, k is equal to di by do, and y is equal to do by 2. Then again substituting these two values in the equation number 1, then M by I is equal to sigma B by Y. Then that M is equal to pi by 32 into sigma B into do cube into 1 minus k raised to 4. This is the equation for bending moment in the case of hollow shaft. From this equation, we can easily calculate the value of outside diameter of the hollow shaft. Then here is the first question. A pair of wheels of a railway wagon carries a load of 50 kilonewton on each axle box, acting at a distance of 100 mm outside the wheelbase. The gauge of the rails is 1.4 meter. Find the diameter of the axle between the wheels if the stress is not exceed 100 megapascal. And this is the figure, a pair of wheel. This wheel C and mounted at is C and D of the shaft AB, and at this particular point, and this particular point, there acts an external load of 50 kilonewton each. 50 kilonewton each at this point, this particular point and this particular point. Okay, then the distance between this wheels is equal to 1.4 meter, and this distance is equal to 100 mm. That distance is equal to 100 mm. Then the maximum bending moment acts on the wheels at C and D. At C and D. Here, while referring this particular figure, we can say that the maximum bending moment acts at point C and point D. Here, this is the shaft, and this point is point D, and this point is point C. Here, acting an external load of 50 kilonewton, and this distance, this small distance is equal to 100 mm. 100 mm is equal to 10 centimeter. That is equal to 0.1 meter. 0.1 meter. This distance is equal to 0.1 meter. Then, while calculating the bending moment, when we consider this particular cross section as xx, and this small distance is equal to smaller tracks, then the bending moment in the right hand side of point D, point D. First calculate that bending moment, then we can select another axis at this particular point x1 and x1, then we can again calculate the bending moment. Again we can calculate the bending moment points between the point C and D. Then when we consider this as the axis, and bending moment along this particular part, this particular axis, due to this external load is equal to that 50 kilonewton. Bending moment along xx is equal to 50 kilonewton into x, and x varying from this point. At this point x is equal to 0, and at this point x is equal to 0.1 meter. Then the bending moment at this particular point is equal to 0. That means bending moment at particular point is we can treat this point as B. Then bending moment at B is equal to 50 kilonewton into 0. That is equal to 0. At this particular point, that bending moment is equal to 0. Bending moment at D is equal to 50 kilonewton into 0.1 meter. That is equal to 50 into 10 raised to 3 Newton into 0.1. That's equal to 5 kilonewton meter. That will be at this particular point D, and that bending moment varying linearly up to this particular point. Here is the maximum bending moment. Then at this particular section, while we considering the section x1, we can treat this overall length, this complete length as x, and we can calculate the bending moment at various positions between the point C and D. Here again another force 50 kilonewton acting at this particular point, and there is a reaction at C and reaction at D, RC and RD. Then due to symmetry we can say that RC is equal to RD is equal to 50 kilonewton, 50 kilonewton. Then the bending moment at x1 bending moment at x1 is equal to this 50 kilonewton into x, 50 kilonewton into x. We can treat that clockwise bending moment as positive. Then this bending moment due to RD about x1 is in the anti-clockwise direction, and we can treat it as negative bending moment. That's equal to, again, RD is equal to 50 kilonewton into x minus 0.1, x minus 0.1 meter, x minus 0.1. Then bending moment at D is equal to, when this x is equal to 0.1, then bending moment x1 when x is equal to 0.1, when this x is equal to 0.1, the bending moment at x1 will become bending moment at D. That's equal to, again, 50 kilonewton into that 0.1 meter. This term will be 0. Then that's equal to, again, 5 kilonewton meter. Bending moment at D is equal to 5 kilonewton meter. This one, when x is equal to 1.5 meter, we will get a bending moment at C. That at this particular point. Then bending moment at C is equal to, once again that 5 kilonewton meter, and that variation is linear variation in between C and D. Again, here bending moment at C will become 5 kilonewton meter. Then again it will become 0 at point A. Then maximum bending moment is at C and D. We can clearly see that bending moment is maximum at point C and D. Here, when x is equal to 1.5 meter, bending moment at C will get. Here we will get the bending moment at C is equal to 50 kilonewton into 1.5 meter. That means this 50 kilonewton into 1.5 meter, x will become 1.5 meter minus 50 kilonewton into 1.5 minus 0.1 meter. That's equal to 50 kilonewton into 1.5 meter minus 50 kilonewton into 1.4 meter. That's equal to this one. Then bending moment at C is equal to 5 kilonewton meter. Okay. Then that bending moment is equal to 5 kilonewton meter, or 5 into 10 raised to 6 Newton m. Then D is equal to diameter of the axle. We know that the maximum bending moment is equal to, pi by 32 into sigma b into d cube. And equating this value into this value and this value, this equation value on the right hand side, we can easily calculate D by substituting sigma b as 100 megapascal. Then D is equal to 79.8 mm. That is the answer. Thank you all.